Hi, today I'm going to walk you through most of the basic functions of XenaManager, which is the free software you use to manage Xena's Gigabyte Ethernet test equipment. So let's jump straight into it. XenaManager is a small Windows application, and you can download it anytime from our website. Just save it onto your desktop and then double-click to launch. To connect to a chassis, simply right-click on New Testbed and select Add Chassis to Testbed. You'll then see a dialog box where you can enter the IP address of the chassis you want to connect to and a password. So now we can see the client is connecting to the chassis, and the first thing it does is show which modules are installed and displays these on the left here. If we click on the chassis, we can see the modules, and if we click on the modules, we can see the ports. I'm not going to use all of these in this demonstration, so let's right-click the module and then choose Unuse to make our testbed easier to work with. For this demonstration, I'm only going to work with a couple of ports, so I need to reserve them. And to do that, I need to go into the Manager menu up here and enter a username. Now I can select the port, and on the right you can see it is free. And if I click Reserve, it becomes assigned to me, so I can begin working with it. These two that I'm reserving now are connected via a switch. So what gets sent by one can be received by the other, if I address it properly using the right MAC addresses, which I'll do in a minute. But like I said, let's quickly simplify our testbed by removing the other module and the ports that we don't need, like this. So now our testbed has just two ports. Of course, all the other modules and ports are still there, they are just hidden from view. I can also add more testbeds or chassis, and they can, of course, be sitting anywhere in the world. All you need is the IP address. The other point I want to make is that there can be multiple connections by different users in different parts of the world to the same test chassis. There are really no restrictions here. If we look here, we can see a couple of colored indicators besides the ports that we'll be using. The yellow indicator shows traffic is being sent. That must be something set up by a previous user, so we'll just clear the configuration by clicking Reset. The green indicator shows the port is in sync, which you can also see over here on the right. That means it is connected to something at the other end of the cable. It drops out momentarily when we reset the port, see how it turns red, and then it comes back on. Okay, now we can start to work with the port, and that's done over here on the right side of the GUI. The first tab is the Port Properties tab. There is some basic information here at the top, and you can see from the interface type that is a triple speed copper transceiver, and it's currently running at 1 gig, etc. You can set layer 2 MAC addresses here and layer 3 IP addresses. But for now, let's go over to the next tab, which is called Streams. This is where we specify the outward traffic, and here the basic unit is called a stream. And if we click Add Stream, we get the stream definition panel, and here we start with the transmission profile by specifying how much bandwidth we want to use. Let's say we want to use 70% of the bandwidth. This corresponds to about 1 million packets per second at the packet size I'm using right now. I could also say I wanted exactly 1 million, which would then correspond to 67.2% of the bandwidth. I could also specify how many megabits per second I want to transmit. There are some subtleties about whether they do or don't include interframe gap, but we won't cover that right now. Instead, let's go back to 70% of the bandwidth. By default, all the packets will be evenly spaced in time with a fixed gap, but you can also make them bursty, and we do that down here. Let's say we want 5 packets at a time. Over on the right, we now get a little diagram illustrating the setting. There are 5 packets back to back at the start, followed by a long gap, and then it starts over again. As you can see, the density of the burst is 100%, and up here we can see the interpacket gap is 20 bytes, which is the minimum allowed by the Ethernet standard. But we can alter that density, let's enter 50%, and see how that affects the gap between the packets and the corresponding figures. The interpacket gap is now 38 bytes and the interburst gap is 128 bytes. But all of that is based on the size of the packets, and that is defined in the next frame down here. So the transmission profile was how much of the bandwidth we wanted to use and how we wanted to use it. Now we define the packets that go into the bandwidth. The first variable is the packet size, and the default is a fixed size of 64 bytes. So let's see what happens when we change it to 100 bytes. Up here we can see that rate has not changed, but the packets per second and megabytes per second has, and so has the packet gaps, which have adjusted themselves to reflect the fact that we want packets that are a little bit longer. And instead of fixed packet sizes, let's choose random, and let's say we'll allow packets between 100 and 1000 bytes. Again, we can see the change reflected up here in the number of packets per second, which has fallen because now the average size of the packet is 550 bytes, and the gaps between the packets and the bursts has also increased. Down here we have the packet editor. Everything starts with the Ethernet header, of course, but after that you can add other protocol segments. So let's add a couple of VLANs and an IP packet, for example. To delete them again, simply click the little cross. The result is a very easy and flexible way of building up the packets exactly the way you want them to be. Now in this demonstration we'll be going through a switch. So let's keep it simple and just send some plain Ethernet packets. To do that we have to set the proper destination MAC address, and that is done by clicking the Ethernet button, so we get this dialog box which gives you a field-by-field view of this part of the packet. As you can see, the source MAC address is obvious. We're on port 4 of the first module in this testbed chassis. Above that we have the destination address, and let's pick port number 5. Down here we have a byte-by-byte view of what goes into the packet. The first 6 bytes are the destination MAC address, and the next 6 bytes is the source MAC address. And then we have ether type, which is a default value. So that accounts for the first 14 bytes that we send out, and the rest is the payload. The payload can be an incrementing pattern of bytes, which is the default, or a PRBS pattern, or we could select to make a user-specified pattern like this, which would then be repeated up through the packet. But for now we'll just stick with the incrementing pattern, and that will then fill up the remainder of the packet, except for an important part at the end, which is the test payload. The test payload takes up the last 20 bytes of the packet before the frame checksum. It contains different sequence numbers, checksums and timestamps that allow us to do a lot of diagnostics. There is also a user-specified part called the test ID, or TID. The default is 1, but let's change it to 17 so we can find it again later. So now we have a complete stream definition, so let's go ahead and start the traffic. The next tab is the Statistics tab, and the first thing we see at the top is the transmit statistics. And we can see we're using 70% of the bandwidth. Here are the rates, 670 megabits per second and around 150,000 packets per second. And over here we have the accumulated number of bytes and packets. There's nothing being received on the port, so let's just minimize these for now. Before we go over to port number 5, just note that the traffic on port 4 is being generated by a single stream, which has a TID of 17, which we set earlier. You could of course have multiple streams, each contributing to the traffic, and we'll look at that later. Now over on port number 5 we can see that it's not transmitting anything, so we can minimize that pain. But it is of course receiving traffic, and it's the same amounts that we saw on port 4's transmit statistics. We can also see that it has registered the TID value, which we set at 17. In the next section we can look to see if there are any errors in the test payload. There are none at the moment, but we can of course simulate errors by going back to port 4 and in the stream definition we can select what type of error we want to inject. Let's make this a little easier to see by dragging the window away from the GUI like this and then minimizing it so we can only see the error injection field. And then we can go back to port number 5, and if we click this inject button we can see that we lost a packet. Now in a real network the switch would have discarded the FCS error, so that's why it says up here that the FCS status is okay. But we know that a packet was lost by looking at the sequence numbers. So if we click this a few more times we'll see some more lost packets. We can also inject errors inside the payload. Let's try that. And over here you can see that XenaManager has registered a payload error. This is a useful feature if, for example, you have a switch that is malfunctioning and damaging part of a payload. You can also look for misorder errors, and if we click the button we'll actually swap the sequence of two of the packets. So again, nothing was lost and nothing was damaged in the payload, but the system did detect a misorder event. Down here we can track what's going on according to a timestamp. If we inject another FCS error, for example, we'll see another lost packet being registered here with a record of what has happened. Let's just do another one. Okay, so that was the errors. We can also look at latency. Again, we use the payload and the timestamp to measure the time it takes for the packet to go from port 4 through the switch and be received on port 5. We measure it in nanoseconds, so this is a 3 microseconds, and we can see the average latency is around 8 microseconds, and the maximum is over 12 microseconds. The resolution is 8 nanoseconds, and the actual accuracy is about 16 nanoseconds, which means that the Xena tester is actually a very high precision instrument. It does assume, however, that the sending and receiving ports are on the same chassis. We can also measure jitter, and jitter is the packet-to-packet variation of latency. It's not surprising that the minimum is 0, because that simply means that two back-to-back packets experience the same latency through the switch, which is to be expected every now and then. But we can see the average jitter is 1 microsecond, and the maximum jitter was just under 6 microseconds. So let's leave the statistics and go over to the capture tab and look at the actual packets. So let's start a capture. As you can see, they're all very simple packets with an Ethernet header and this ether type. And over here we can see the incrementing pattern of bytes up through the packets. Over here we can see the lengths of the packets are changing because we ask for random lengths of between 100 and 1000 bytes. At the bottom here we can see a capture graph which illustrates the length of all the packets. If we hold the mouse over one of the short packets, we can see, for example, that this one is 209 bytes, while this one, the long one, is 973. We didn't capture much data, which reflects the limitation in the capture buffer size, but if we limit ourselves to capturing, for example, the first 40 bytes in the header, we can capture much more data, as you can see down here. We can also look at the interframe gap. Down here we can see the gap is just 20 bytes, so the packets are being received back to back, whereas up here the gaps are quite long. This graph shows quite clearly how much of the traffic gets distorted just by going through a simple switch. So that was the capture tab. We can also look at histograms, where we start counting the packets based on different criteria. We could, for instance, look at how long the packets are. Let's zoom in so we can see more clearly, and now we can see it starts at 100 bytes and it tops out at 1000 bytes. And we can see there's an even number of lengths in between. If we hover the mouse over any of the bars, you can see the details of each packet, and down here at the bottom you can check what it is you're looking at and the range, from 44 bytes up to 1051. Of course, some of this traffic might have been generated by the switch itself, like this very short packet. Let's make another histogram, and this time we'll look at the interframe gap for the transmit packets. Of course we can't do that on port 5, as that isn't transmitting any streams right now, but we can if we go back to port 4. So if we start the histogram now, we can see two distinct peaks. One is 753 bytes, which is the burst gap, and the other one is 140 bytes. And if we go back to the stream definition, let's just close this window so it goes back into the GUI like this. Now you can see an interpacket gap of 142 bytes and an interburst gap of 753 bytes. If we quickly go back to the histogram, we can also see that 80% of the samples are on the left of this particular point on the histogram, and that's because we have 5 packets in each burst. Let's now go back to port number 5 and let's look at a histogram showing the received interframe gap. Again, we see very distorted results for the traffic caused by its passage through the switch. Okay, so now we've looked at the statistics, where we can see all the numbers, capture, where we actually look at the packets, and the histograms, where we can start counting the packets. There's also a tab for testing 40G and 100G ports, but I'm going to leave that for today and cover that in another demo. There's one more tab that I want to show you, and that's the last one here, called Global. So far in the demonstration, we've kept things very simple by only looking at a couple of ports and a couple of streams. Nevertheless, there's been quite a lot of clicking around to see what was going on, so obviously if you have a big testbed, that would be impractical. So that's why we use the Global tab. We can drag the control panel out here, and this lets you have one window to start and stop everything. Plus you can quickly see how long the traffic has been running. Down here we have some port level global statistics where we can see all the figures, which again means we don't have to skip backwards and forwards to view the results. There's also a stream view where we can, for example, see stream number 17 here. Of course, you only really appreciate the value of this tab when you have a lot more streams and a lot more ports, etc. in your test bed. So let's go back to the streams on port 4, stop the traffic, and add a stream or two that are a little more complex. We'll minimize the stream we have already, and we'll click the button to add a new stream. The stream ID of 18 is fine, and we're also okay with 10% of the bandwidth. So let's go down to the packet content and say we want fixed size packets of 500 bytes, and now let's put something a little more interesting into the packets. Let's start with some IP testing and add an IP packet. Now by default there's nothing inside. So let's go back to the port properties, and here you can see there's a place where we can enter a test port IP address. So let's say 10.0.0.7, and then it'll ask us to confirm that we want to modify your existing stream to use this address, and yes we do, so we click yes. Now if we go back to the stream and look inside the packet, we can see it uses the address we just added. It's up to us where we want to send the packet, so let's try something like 10.0.0.37. It's worth noting that you can also do this editing directly in hexadecimal. And if we look here, we can see the source address and the destination address. Usually most people just use this tool. Now of course, with IP traffic, we'll still have to address the packet at layer 2, which means we need to enter the destination MAC address. And this is where you would typically use the ARP protocol, and I can do that by clicking the ARP button. But, as you can see, there's no response. So the tester has tried to send an ARP request from the source MAC address to the destination, and it didn't get a reply. But we can easily fix that by going to port number 5, and via the Properties tab, we can now enter the MAC address that we selected earlier, i.e. 10.0.0.37. We can also tell it to respond to ARP and ping requests. So let's see if that worked. Let's go back to port number 4 and try to send an ARP request. As you can see, XenaManager tells us that the test port received a reply to its ARP request, and that this address has now been set in as the destination MAC address. And we can, of course, confirm this by looking down here at the hexadecimal value. We can also do a ping request, and there we can see the response. So this shows you how to do the IP traffic setup. We use the outgoing ARP and ping buttons on the transmitting port to set the outgoing MAC address. And via the Properties tab on the receiving port, we use these checkboxes to to enable a response to incoming ARP and ping address. And this is also where we enter the MAC address. Up here there is also a little checkbox called MAC training that we can use, which makes this port announce the fact that it has this address to the switch. The port is not transmitting anything, so the switch has no way of knowing that we have set this MAC address, but if we enable the MAC training feature, we solve that problem. Of course, this is standard procedure at layer 2, just as using ARP and ping is standard for layer 3. Let's go over to the stream on port 4 and start the traffic, and then if we click over to the statistics, we can see that we're using 80% of the bandwidth, which is made up of 2 streams, one generating 70% of the traffic and the other sending the last 10%. We can also see down here that we have transmitted 2 ARP requests and 1 ping request. If we go down to port number 5 and look at the statistics, we can see a second TID has shown up in the traffic, number 18, and it has its own counters for errors, its own latency measurements, and its own jitter measurements, etc. If we go over to the capture tab and start a capture, we can stroll down through the results and we'll find an IP packet. Of course, 70% of the traffic are these short little Ethernet packets, but if we look at one of the IP packets, we can see that it's one of the ones we sent. We can use the capture function to also do some filtering. We can, for example, filter out everything except the IP packets, which means we only want to see those streams with the TID of 18. Now you can see that the only data being shown are our IP packets, as the rest gets filtered out. And the last thing I want to show you here is over on port 4, where we'll stop the traffic and look at the modifier field. This allows us to generate packet by packet variations within the stream. Without this feature, every packet would be exactly the same content inside the header, except for the length, which we have set to random, of course. But now we can take a modifier and say we want to put this on the source address. Down here you can now see a little black line, which is the position of the source address of the IP packet. Down here it says it is at position 26 and that it's using 2 bytes of the mask. We can cut it down and say we only want to modify 1 byte, and that it should be moved right to the end of the address at position 29, so it'll no longer just be 7. So let's tell XenaManager that we want to modify from value 10 in steps of 5 all the way up to 100. We could of course add more modifiers if we wanted to, but let's just stick with this one for now. So if we start the traffic, go back to port number 5 and do a capture, and look inside some of the packets, we'll see, for example, that this one used 95 as the source address, and the next one used 100, and the next one again used 10, which means it went from 100 back to 10 just as we told it to. So the point is that with this one stream we have quickly and easily been able to simulate a series of source IP addresses, which is just one of the many ways we can use the stream definitions to generate complex traffic patterns. In the last section of this video, I'd like to go into some of the other aspects of using XenaManager to control the chassis and perform tests. Everything we've done so far has been stored on the chassis. The XenaManager client runs on your desktop, but it writes to the chassis. We can easily demonstrate this by simply shutting down the program and then starting it up again. As you can see, XenaManager remembers which chassis it was connected to and the testbed we had defined. However, if we turn off the chassis, we'll lose the configuration. And to avoid that, the solution is to right-click the port and choose Save Port Configuration. You can then save a small text document onto your desktop. So let's try to open it now with Notepad. At first glance, it might look a little cryptic. But if you look a little bit closer, you'll see it matches the settings in XenaManager. So if we look at, for example, the packet length down here, we can see it says random 100,000. And if we look at XenaManager, we can see for this first stream that the packet length should be random with a minimum of 100 bytes and a maximum of 1,000 bytes. The same for the other settings, like the payload type, which is set to incrementing. And this means that we can also edit this file to change the settings on the chassis. So let's change the random packet length to be a maximum of 1234 bytes, and then save that change. The next step is to go back to port number 4, right-click it, and choose Load Port Configuration. Then we find the text file again, and just watch what happens to the value in the max field when we click OK. So this is a very simple and direct way of configuring the chassis. This function is also available at the test case level, which means that instead of just changing the individual port settings, you can configure the whole test bed. And the way to do that is to go up to the top, open the testbed menu, and select Save Test Case. Let's just put that on the desktop too, and as you can see, it's saving all the settings for the modules and the ports that are active. We can also delete the chassis that we weren't using by removing it from our testbed and then saving the new testbed configuration. Do we want to write over the old file? Yes, we do. And now it just saves those two ports that belong to our testbed. So a test case is a configuration of all the ports in your testbed. Again, we can use Notepad to view and edit the file. It has a different suffix than the one before. This file is an XTC file, which stands for Xena Test Case, whereas the port level file was an XPC, which stands for Xena Port Configuration. When we open it up, it looks pretty much the same, but it simply lists the ports in the order they appear on the chassis. So at the top you can see information about which chassis, test module and port we're looking at, and then if we scroll down we'll see the second port down here. The rest of the settings are the same. This syntax is the same we use for scripting, and if you're interested in learning more about that, you can download a detailed guide from our website called the Xena Scripting Specification. Finally, if you have any questions about using the XenaManager, there is also a link up here to a help manual, which is provided in a PDF format. It basically goes through the whole GUI in much the same way that I've done today. This manual is also available on our website, of course. So that's the basics of using XenaManager. There is, of course, a lot more you can do with the program, and if you'd like a personalized tour where we go through specific features and functions that you are interested in, please contact us and we'll be happy to set up a live demo.